Welcome back. In this video we are going to look at hypothesis testing with t-distributions because we are not going to have our standard deviation, and we will also be working with small sample sizes. Now I'm going to go through the problem and kind of list out some step zero, and I also have some space up here I want to use, and this is going to be kind of cool for you to see how the calculator can do some of the work for you or not. This statistics students believe that the average score of their first test is 65. Boy, that sounds like a null hypothesis to me. So for step zero, I'm going to put down mu equals 65, and let's just get to the null hypothesis. Null hypothesis is going to be the mu equals 65, okay? Now, the statistics instructor thinks that the average score is higher than 65, and boy, that sounds like an alternative. All right, so this is mu greater than 65. So he samples 10 statistics students, so this is my sample size of 10. Now that is another key indicator that we're probably not dealing with a z distribution. We're going to look at instead of the z chart, the t charts, because we're going to have 9 degrees of freedom here. And here are the actual scores. Now, what I've done okay, let me finish this up before I talk about this list of data. He performs a hypothesis test using a 5% level of significance, so that is my alpha. My alpha is 0.05. My confidence interval would then be 95%. I'm 95% sure of this information, or I want to test to the 5% chance of making a mistake. Now the data is assumed to form a normal distribution. This can kind of be a sentence that will get us out of step 2. Step 2 is a test to assume normality, so because this sentence is given, we could literally skip step 2. But I want to just kind of like go into like the fact that we have this list of data. I actually typed this in already, and you will do the same. So in list 1, I have the data. You can see that the scores are from 65 all the way down to the last one here listed at 71. And I'm going to perform the shortcuts of stat, write, and then hit enter. Now, obviously I want list 1, and the frequency of the list is default and fine, so I'm going to click on calculate, and this is going to give me the average, or the x-bar, which wasn't given me in the problem, and the standard deviation. The standard deviation I'm going to use is with Bessel's correction, or the capital letter S, and this is because of the low sample size. So I need to write down in my notes here that important information, that this optional step of going stat, write, and then enter will give me to my one variable statistics. So I now have my x bar, and my x bar, which I can use in step 0, is going to be my sample average and my sample standard deviation. And my sample standard deviation, I'm going to use a lot of decimals here. Let's go 3.1972, on and on and on. You'll notice that we did not have a lowercase sigma. That's a huge indicator that we are not using a z-test. We had to get the standard deviation from our sample and not from the population, so therefore t-test it is. Now step 2, again, I could tell you that we are skipping this step because we had a sentence, even though this was under 30, the sentence has normal distribution. But what if that sentence wasn't there? What would we have to check? We would have to check for an outlier. Now, back up to the one variable statistics on this screen here, you can actually click down to see what your Q1 and your Q3 is. The Q1 and the Q3 is 65 and 70. Now what I'm going to do is I'm going to put that off to the side here because, again, if we didn't have this sentence, we'd have to check for our outliers. So Q3 is equal to 70, and Q1 is equal to 65. Now, if I ask for this on the test, you do have to do an outlier check here. So our outlier check is to take your IQR, and your IQR, then you'll multiply it by 1.5, and add that to Q3 to see if you have an upper problem or an upper outlier. So 70 plus the IQR here, and the IQR is the distance between these two. So 70 minus 65 is 5. So 70 plus 5 times 1.5 is going to give me an answer of 77.5. And we don't have any test scores above 77.5, so we've checked there. Now, the Q1, we're going to subtract our IQR times 1.5 from this one. Okay, so here we go. So my IQR is 65 minus 5 times 1.5, and that gives me an answer of 57.5. We don't have any score below 57.5. So what we have is no outliers. So since no outliers, we can assume normality. And what's great about that is that we can now take our X bar and connect it to our normal distribution, which has our standard deviation of 65, and our our average of 65, and our standard deviation is going to come from our sample here, and the sample is going to be 3.1972, and divided by the square root of our sample size, not our degrees of freedom, but the sample size. Now, what I just did in this yellow highlighted area is kind of cool academic. It's not really necessary, but it just shows you that we've actually done this before. We did this back in the previous chapter when you looked scores up on the T-chart. Well, let us go and let the calculator do the work for us in step 3. Now, what's kind of handy is that you typed all of that information into the calculator, which is pretty sweet, right? So when we go to our clicking on the stat and then clicking twice over to the tests, and I'm not writing down these steps because I assumed you watched the previous video on z-testing, you click once down to t-test and hit enter. Now let us click enter here on stats, because you can choose either data or stats. I'll show you in the next example what would happen if you click data. But now I can type in my average, and this is the average that is the null hypothesis average, 65. Now you'll notice that, look, the 67 was already typed in there, and that's not because I did the problem ahead, it's because the calculator saw some data in list 1 and said, hey, do you mean this one? And yeah, we do. How about the standard deviation? Look at that big ol' SX. And that is what we need, and it uses all the decimals. And our sample size, wow, this calculator is super cool. Now from the previous video, I had the correct inequality already listed, so please, make sure it's on the inequality you want based on the null hypothesis up above here. You see the null hypothesis was equals, then the alternative, we want greater than the alternative, okay? So make sure that this matches the alternative. Now, your book is going to ask you to click on calculate, then click on draw. Let's just click on draw. Get the problem done just a little faster. Oh, look at that beautiful T-curve. If you really analyze that T-curve versus the Z-curve from the previous video, you'll notice that the tails are bigger and it's a little deflated up at the top because the T-chart uses a family of curves. And instead of, printing off 26 or 20 some curves for all the ones you're going to use, the calculator can just render it for you. So this is super great. All right, so we've got a t-value of 1.9781 and a p-value of 0.396. So let's write that down for step 3. I'm not going to list all the steps here because you've been through the previous video. So here's our t-value, or t-score, which is like a z-score, but with a different in the family of t-curves. And this is our p-value of 0.0396. All right, let's get to that picture here. Now I'm going to look at my calculator off screen and draw my normal curve. Okay, try to be a little bit more accurate with the bigger tails at the end of our t-curves here, but again, you're not an artist, so I don't need to have the perfect rendering. So I'm going to plant my flag at that positive t-value, and that t-value was at 1.9781 standard deviations away from the norm, because this would be the norm. And if you're thinking to yourself, man, 2 standard deviations away from the norm is pretty far out, yes, you just witnessed a rare event, because the situation here is that your p-value, you got to compare that to your alpha, and your alpha in this case was 0.05. This was just the default normal alpha, and then your p-value was 0.0396. Now remember, your alpha is your chance of making a mistake, and if your rare event had a less likely event of happening than making a mistake, you're going to question the null hypothesis. And ladies and gentlemen, you can see that 3.96% is less than 5%, so this means we reject the null hypothesis. Because according to the rhyme, if the p-value is low, you got to let the null go. So this brings us to our conclusion statement, which needs to have an inequality. Since p is less than alpha, you need to have that inequality. I need to see why you continue with this statement. We have sufficient evidence. We have sufficient evidence to reject the null hypothesis. Okay, you gotta have that inequality there. Because if you just say we have sufficient evidence or we do not have sufficient evidence, I don't know why. I mean, you're just saying like, oh, there's stuff in the problem that says we can do this. What in particular? Well, literally this. This is the sufficient evidence. We had this event was more rare than making a type 1 error. So we're going to reject the null hypothesis. All right, so here's the next problem. And you'll see that I actually don't have a large amount of space in step 0, because we're going to use the data function on our calculator to help us out here. Okay, so we have basically some industrial work here with glass. It says the National Institute of Standards and Technology provides exact data on conductivity properties of materials. The following are conductivity measurements for 11 randomly selected pieces of glass. Okay, keep in mind that these glass, they all should have a conductivity of 1. All right, now that is going to be my mu. The glass should have a conductivity of 1. So what we're seeing is a sample set of pieces of glass that have distances off of 1. So we're wondering if that's manufacturer defects or, you know, something like that. So is there convincing evidence that the average conductivity of this glass is different than 1? All right, so there's our null, right? Our null is going to be 1 from our given assumption, and here's our alternative. Is there convincing evidence that the average conductivity of this type of glass is different than? Well, that is going to be not equal to. The is different than is just asking if it's above or below. So, assume the population is normal. Awesome, we can skip step 2. But we really don't have a lot of information from this problem other than the data, raw data itself. We have our sample size of 11, if I counted those up, which means 10 degrees of freedom. All right, and we're going to have an alpha of 0.05, which means our confidence interval is 95%. Okay, 0.05 is the default. If it's ever not listed, use a 0.05 as our default. So step 2, again, we can skip that because we have, even though the sample size is under 30, we have normality. And the normality was given in the problem, see above. So we don't have to do the outlier check. Now again, on the test, if I ask you to do the outlier check, please do the outlier check. This is something you've done in previous units. It's kind of nice to repeat it anyway. So let us get into step 3, which is going to be to use the calculator. Now, I did actually, to save some time here, load that information on the calculator. In fact, I can just load it up here by clicking second 5, and there it is. There's our data. And I'm just making sure it's all here. Got 10 pieces of data. So now I'm going to click on Stat. I'm going to click on Tests. And then I'm going to click on T-Test. Okay, so let's go check the mu sub 0. Our mu sub 0 here is going to be our 1. Just 1. Now our average. Oh no, see, it doesn't actually have the average. It has the average from the original problem. So maybe we should go and click on Data. Click on the data screen. Blam. If you click on the data screen, now it takes the list in list 1 and the frequency, and it's going to do all the work for us. So we didn't have to type in the one variable stats like we did before. So that's quite nice. So you can save yourself some time by clicking on data, and it will take that list 1 data and do it for you. Keep the frequency as 1. We're not going to double or triple our lists. Now we want two-tail. We want two-tail because our alternative hypothesis says we just want it to be different than 1. Okay, so let's go to draw, and you get to see a two-tail test. All right, you can see that we have 2 shaded regions, which is pretty great. And our t-value is 2.01, and our p-value is 0.717. Okay, so here we have step 3, putting down our important information. Our t-value was 2.01, and our p-value was 0.0717. Okay, so let's go to our picture. Okay, so here's our picture. All right, you can see I kind of drew the ends of this. The t-curves have more area at the tails than they do in the center. So here we have our flag. Our flag is going to be planted at 2.01 because it looks like all of these glasses they leaned higher in terms of their reflection, or their, I'm sorry, not reflection, their conductivity. So their conductivity was leaning more positive than negative. If you look at all the data, you can see that there were more numbers above 1 than below 1. So we landed here, and our probability of landing in both of these zones, so in both of these zones added together, the chances of landing in those zones are 0.0717. So by giving a two-tail test here, this actually increased our chances of landing in these zones. So this is going to actually decrease the chance of us rejecting the null hypothesis, because we're going to compare the p versus the alpha. And the p was 7.17%, and our alpha was only 5%, so this is greater than. So, according to the rhyme, if p is high, you gotta let the null fly. So since the p-value was greater than alpha, again, you need that statement right there for the take-home or the paper pencil versions of these tests. Since p is greater than alpha, we do not have sufficient evidence to reject the null hypothesis. So you now do not reject because of this statement. Do not reject. Okay, here's something that I want to talk to you about. What would happen if you change the confidence interval or alpha? So what if we just say, instead of being an alpha of 5%, what if we just said we want alpha to be 10%? Huh. Well, now the p, which is 0.70717, and the alpha, which is now 0.10, now we have a different conclusion, right? Yeah, by just changing the alpha, I can get the result I want. This is a very clever way of making a different conclusion just by messing with the alpha. So be aware that statisticians can do that. We can mess with the alpha to get the result that we want. Now, it's really hard to do. It's really hard to do if your data isn't already pretty far away from 0. All right, so this in case was 2.01. So if you find that you can't like change the alpha to like 80% or 90%, that would just be why would you want to do that? That would be statistically dishonest. But still, moving the alpha from 5% to 10% can have a completely different conclusion. Also, what if we just made this right tail instead of two tail? If we made it right tail instead of two tail, we would literally just get rid of this left side, and the p-value would be half as big. I can show that to you just by going to tests and going to the t-test that we just did and making this right tail. Well, now if we just make it right tail and graph it, whoops, hold on, not graph. You have to hit right tail and hit enter, not graph. Maybe it was good that I showed you that mistake so you don't make it by accident. So click on draw. So this is the right tail version of what we just did. So again, our t-value is exactly the same, but our p-value is cut in half because we don't have the second tail over here. Well, shoot, since our p-value is cut in half, we don't have that tail over there. Gosh, we now have a different conclusion, right? So by making this right tail, what we now have is this p-value, which again, as I said, stays exactly the same, p.0717, but now my alpha is, sorry, not made a mistake there. My p-value, which is now cut in half, 0.0359, and my alpha, which I'll go back to my 0.05, you can see that we now have another different conclusion. So this end of this video, which I'm sorry took a little bit longer than the first video, shows you that if you change the alpha or change the amount of tails in the problem, you can get a different result than before. And that right there is a little bit of sneaky statistics. But that sneaky statistics is something, maybe in your higher level classes you should analyze a little bit more. But it goes to show you that sometimes with even really solid statistical information, we can the human element is there. The human element is there to mess with it sometimes. So I just wanted you to be aware of that. Well, thank you for watching this video, and we're going to move on to the last video here where we're going to be testing proportions using the one proportion t-test here, or z-test here, the one proportion z-test in the next video. Thank you for watching.